Welcome to TubeTime on CoolDudeClem's electronic workshop. I'm not going to talk like that for the rest of the video. I was just doing an impression of how I normally seem to sound in my videos. Anyway, today I'm going to let me repeat that, attempt to build a vacuum tube Tesla coil. And I know I don't have the best of luck with these, so I have no idea how well this one's going to work. It might work great. It might not work at all and just give me a red hot tube. And just one more thing before I start. If you're wondering why I sound a little different, well, that's because I'm not happy with the original running commentary from the video. Not to mention that later on, I forgot to have the microphone connected. So, yeah, have to redo the commentary. Also, I hate the way the acoustics in my room make my voice sound all boomy when I'm not close to the mic. Alright, so here are all the parts that I'm going to use. This is my primary. It's about 30 turns. Actually, it's about 35 turns. Tapped at every turn. This is my feedback coil. Forgotten how many turns it is, but I think it's somewhere around between 20 and 30, something like that. And this is a brand new secondary that I've made. Again, I've forgotten how many turns it is, but I've wrapped the whole thing in tape to protect the coil, and for my top load and breakout point, I'm just using a screw, but I think it should work good enough. Now this thing is my resonant capacitor. This is a capacitor that I made, and I chose to make it about 1 nanofarad. Actually, when I measured it, it's about 1.2 nanofarads, so it's pretty much how I wanted it. Because in most Tesla coils I've seen, they've either used something higher than that, or something lower than that, or something that's very close to it, so, you know, I decided for average, I'll just make it 1 nanofarad to see how that works. Here's my grid leak circuit. It's just a 60 watt light bulb with a 3.3 nanofarad capacitor across it. And here is the serious part of the device. The part that's going to do the switching. A GU50 valve, or GU50 tube, depending on what you want to call it. So I'm going to tune it in the conventional way by using a fixed capacitor and connecting the power to each tap on the primary and see where it works best. And if that doesn't work, then we're going to do it my way, because I've got some theories and ideas I want to try out. Look at this. I build it. Okay, this is about the 40th time trying to record this part of the commentary, so I hope it goes well this time. Anyway, here you can see the Tesla coil all wired up. I've got my primary sitting on a couple of pencils so it doesn't arc to the secondary's ground wire. And I've also got this long wire connected up to my scope, and that's not actually connected to any part of the Tesla coil circuit. That's just being used as an antenna, and that will pick up any output from the secondary, and we'll see it on the scope. So anyway, the tube is all warmed up and ready to go, so I'm going to do a low power test with this 600 volt power supply that I made, and we'll see how well it works. We'll probably have a catastrophic failure somewhere. Most likely my homemade capacitor will blow up, but we'll see. Okay, here we go. I'm plugging it in, and nothing. Okay, well, not completely nothing, because I did see a waveform on the scope, so it is oscillating, but maybe my feedback's the wrong way around, so I'm going to flip that over and see if that helps. Okay, so the feedback is round the other way. So let's plug in the 600 volt supply again, and let's see what we get this time. Still nothing. So, obviously, it's not tuned. So, I'm going to try every tap on the primary, and then I'm going to come back when I found what works best. Well, that was a waste of time. I tried every tap on the primary, and it seems the further down I go, I get less and less output. And I also tried it with the feedback both ways round. So I've decided that I'm gonna get to the bottom of this and find out why it wasn't working. So I took some measurements, did some calculations, and it turns out with this primary and this capacitor, I will never get good output. Never. You see, the thing is, the key to making any vacuum tube Tesla coil work well is resonance. The primary has to have the same resonant frequency as the secondary. And that is why this coil isn't working. The resonance is completely out. Okay, I've just decided that I'm going to sort of start over again. Okay, so first things first. In the previous video footage that I shot, I was not happy with the commentary, and later on I forgot that the microphone wasn't connected. So, anyway, back to live commentary and stuff. So, I'm using a different secondary, a different primary, and here's another nice thing about this coil. I can actually move the primary and the feedback up and down and find where the best magnetic coupling is. So this coil, when I've got the magnetic coupling right and when I've got it tuned properly, this thing should work really, really well. But first, before I wire this up to any Tesla coil circuit and have sparks flying everywhere, I'm gonna make a few measurements. Need to find out what the resonant frequency of the secondary is. And it's got to be done with the secondary grounded and with the feedback coil present and also grounded, because all of those and what you had for breakfast last Tuesday, all of that is going to affect the resonant frequency of the secondary. There's just no getting away from it. That's just the way it is. So anyway, to measure the resonant frequency, I've got this little signal generator that I made, connected to the primary through a 1K resistor, and you can probably make it out a little better this way. You can see the resistor connecting this to the primary. So all I need to do now is I just need to tune this till I get the most output. It's already tuned on to where I get the most output, but just to show you again, there we go. So right about there we get the best output, and that's being picked up by this long piece of wire here. And as you can see on the meter, our resonant frequency is about 541 kilohertz. So now what we need to do is make the primary's resonant frequency the same as the secondary, and we can do that by adding a capacitor across the primary, but not just any capacitor. We need to find out exactly what capacitor we need, and the first step in doing that is to measure the inductance of the primary. And again, we need the secondary inserted and grounded, and also the feedback coil needs to be present and grounded as well, because like I said before, all of that's going to be there anyway. That's all going to affect the inductance of the primary. So let's just see what the primary is. This is about the best way I can do it. Let me show you on the camera. The inductance of our primary is 47.13 microhenry. So now we know the primary's inductance and the secondary's resonant frequency. We can work this out, but rather than going into some long, complicated formula, I'm just going to go to this site here, plug in the values, and let's see what we get. So I'll start with the inductance of the primary, and now I'll just enter in some random capacitor, let's say 2.2 nanofarads. And now we'll be able to find out what the primary's resonant frequency will be if I were to use that capacitor. Well, that's pretty close, and that's given me an idea. Okay, let's try 1.6 nanofarads. 579 kilohertz. Well, Okay, I've got a great idea. A variable capacitor submerged in oil. Yeah. And no, I haven't gone crazy. This is actually a pretty good idea because, for one thing, the oil is going to increase the maximum capacitance. So if I turn this up all the way, you can see it's about 2.4 nanofarads now. And out of the oil, it was about 1.3 when I had it up all the way, so that's pretty good. Also, the oil is going to stop any sparks across the plates because we don't want any sparks there. That's a bad thing. We want sparks here. And the good thing about this is that the amount of capacitance that I need is well within the range of this variable capacitor, so I can just dial in the exact capacitance that I need. Alright, so here we go. The tube is already warmed up, and I've decided that instead of a light bulb, I'm just going to use these resistors, because I've seen other circuits that use this tube for this kind of thing, and generally a resistance of about 100k is used here. Well, a light bulb's not 100k. It's more like 100 ohms, something like that. Okay, real dumbness on my part here. I just recorded this thing running, and I didn't think to check that the camera was pointed at it. So I'm going to have to shoot this bit all over again. So anyway, let's see it running. Alright, so let's plug this in. And already we're getting something. So I'm just going to adjust the capacitor to where we get the most output, which seems to be right about here. And there we go. It's working. And look at the frequency. 551 kilohertz. Just like my calculations and my measurements predicted. So I think the very next step is to ramp this up to a microwave transformer. But just before we do that, I want to show something kind of weird. Now, I've flipped the secondary. I've flipped the feedback round, so it's now the wrong way. But surprisingly, when I plug it in, it still oscillates. And if I tune this, we're now getting output. It's about the same as what it was before, and the frequency has gone up to 782 kilohertz, which is kind of weird. However, I'm not going to run it like that because, well, for one thing, it's not at the right resonant frequency, and you didn't get to see the output on the scope, but the output picked up on the scope wasn't as strong, and that was probably pushing more current through the tube than was needed. So, yeah, I'm going to flip the secondary round, and then we're going to try this on a microwave transformer. Don't know if the tube can take it, but we'll see. Also, I don't know if my secondary will be able to take it either, because in the previous run, although you didn't get to see it, my secondary started smoking. It does get pretty warm. If I'm going to run this off a microwave oven transformer, it's going to have to be very, very briefly, but I'm going to do it! Because I'm crazy. Okay, it's time to power this off a microwave oven transformer now. But not a wheelie little pissant transformer like this. I mean a real microwave oven transformer. And this is how I'm going to power this transformer up. Now this may look like an ordinary power strip, but it's not. I rewired this. So instead of the two lives being connected together and the two neutrals being connected together, it's completely different. Now, the live from the plug, or the hot, depending on what you want to call it, as normal, goes along the wire and into this pin here, but it's not connected to this pin. The live is only connected to this pin, and these two pins here are connected together, and the neutral is connected to this one. The only thing that is still original is that the two earths are connected. And you might have noticed that one pin is labeled ballast, and the other pin, one socket is labeled ballast, and the other socket is labeled load. This is so I can plug in any kind of ballast I want, because I don't have a variac. So what I'm going to do, to limit the amount of power going into the transformer, I'm going to use a ballast instead, which is my heater for my room. So I've got 3 different levels of ballast I can use from that heater alone. So I will just plug the microwave transformer into the socket marked load, the heater into the socket marked ballast, and that's it. We're done. All I need to do is plug that into the mains, and it's set up. And just for those of you curious, this is what's inside. As you can probably tell. See, this live only goes to this pin here. The neutral only goes to this pin here. And these two are connected. So now this is just with the heat setting on 1. So we should only get little tiny sparks. As you can see. But if I turn the heater up, let's set it on to a slightly higher heat setting, we are going to get much more output. Well, we should be able to. Yeah. Oh. We don't want any fires. This is with the heater on its maximum setting. Now, if this was plugged directly into the mains, we would be seeing some really big arcs. Can pull that out pretty good. At the end, the wire's still glowing. Okay, and we're about ready to start. The tube is all warmed up. The filament's being powered by this transformer here. Just got loads of different wires on it, and pretend you didn't see that plate with the remains of cake on it. But anyway, we've got our big microwave oven transformer here. We've got the ground wire connected to the circuit's ground, and that's connected to the mains as well, the mains ground. Got a diode rectifying the output from the transformer to DC, and that's going into the primary of the coil. And also, the output of this diode is going into this resistor, which then goes into the second grid of the tube. And I put this capacitor between the second grid of the tube and the ground because I want to keep RF off the second grid. Well, I'm sure I've confused you enough now, so here's a schematic to clear things up. Okay, we're hot. Okay, I'm just going to turn this on to low power. Alright, that's low power. It might not be tuned properly. Let's just adjust that. Okay, I'm going to try slightly higher power. Well, that's slightly disappointing. I was expecting to get a bit more out of this. Let's just do that in the dark. I'm not going to put the full power of the microwave oven transformer through this because I really don't think that tube is going to be able to take it, but I'm going to try this on the 1 setting again. Okay. I just realised that you can barely see anything. This is the 2 setting. That's slightly more, but that's not much more than we were getting with the 600 volt supply. I'm actually quite surprised about that. Okay, I'm going to try it on the 3 setting.
Oh, it flashed.
Well, I don't know if you saw that, But I saw an arc in that too when I had it on the full thing. And my voltage detector pen lit up. I don't know if you saw that either. It flashed. Something arced in there. Okay, kind of disappointed with that. I really thought that was going to do some more, but I wouldn't be too distraught if it turns out that tube's no good anymore. I've got a spare one. But we all know this is small potatoes, right? I think it's about time we moved on to something a little bit more powerful.
The miscellaneous components, which is everything, all the mechanical parts, all the ones on my easily forgotten list, added up to about 107.
Welcome to TubeTime on CoolDudeClem's Electronic Workshop. And yes, just to piss off everybody who thinks that a resolution less than 4K is potato quality, I'm doing this in standard definition. And also because it was as I'm doing tester coil videos, I cannot use this camera because you know what this camera does when I use such a device. So anyway, what I'm going to do today is get this out of the shot because that's got nothing to do with it. Because I'm going to make another tester coil, but I'm going to do it the CoolDudeClem way. So I've got a primary here. This is the one I used in my solid state tester coil, which I've just modified. As you can see, all I've done is I've removed the top load and just left the breakout point. Because these things seem to work better without a top load when doing vacuum tube tester coils. And this is just a low power test, which is why I'm using my GU50, my one remaining GU50, because if you might remember I toasted the other one in a previous experiment, hooked it up to a microwave oven transformer, and that was the end of that. So this one is only going to be powered off 650 volts. At the most, from this power supply that I've made. Now this is just one that I've knocked together. I have no idea what the resonant frequency of the secondary is, or what the inductance of the primary is, or anything like that. I mean, we could do a lot of complicated calculations, but you know what? F it. We're gonna do this the CoolDudeClem way. So first of all, let's just turn it on and see if it works. I've got my meter here, so if we get a very low voltage going into the circuit, we'll know something's wrong. So let's see if it does anything. It's all warmed up and ready to go. And nothing. Now we're only getting about 386 volts into the circuit. So, the circuit's pulling a lot more current than it should do. So, I think my feedback is the wrong way around. So I'm just going to reverse that. Right. Feedback coil is connected the other way around now, so let's see if it does anything this time. Well, the voltage is a lot higher. We've got 563 volts. It doesn't appear to be doing anything. But maybe we can persuade it. Right, first of all, let's just test that it is producing an RF field with this compact fluorescent light. Alright. See if we can get any spark off this. Okay, we can draw an arc. Oh, and we do have a little bit of breakout now. So, that tells me I've got the feedback the right way round. So now we know that works, we got to find out the right amount of capacitance to use across the primary. Now these are the capacitors I'm using. 10,000 volts 2.2 nanofarad caps. So let's see what we get if we take one of them out of the circuit. So that's now only 3 capacitors. Right, I'm going to start the circuit again. Let's see if we get any breakout. Okay, we don't have as much breakout this time, hardly any breakout. Still getting a spark, which you probably didn't see, because I don't know if I was filming the camera at it, so let's go down a little bit with the capacitors. Right, let's see what we get with just 2 capacitors in the circuit. Oh, it's having a hard time doing anything now. So now we're going to go down to just 1 capacitor. Oh, and do note, I am turning the power off before I do anything. So this is just 1 capacitor. And yes, to the 1,000 people commenting in, I know these are not the best capacitors to use, but they're all I have. So you just have to deal with it. Right, this is with just 1 capacitor. And it's barely working at all. So I think we need more capacitors. Well, I said I was going to need some more capacitors, so I think this should be enough, and in fact it is, because I've only used 6 of them. 6 capacitors, and we're in resonance. Now I am going to ramp this up with a much bigger valve, so not going to be using this wheelie little thing for too much longer, but these are just the low power tests. So you're not going to be staring at little wimpy sparks for much longer, but what I want to do is adjust the secondary's height, because the position of the secondary relative to the primary is going to affect the magnetic coupling. So I can move this up and down, and I should be able to find a point where the magnetic coupling is at its best. Now the thing is, I did try raising the primary, but that didn't really affect it in any positive way. It actually made the output a lot worse. So instead, I'm going to start with the secondary, right at the bottom, and then raise it up a little bit, test it, raise it up a little bit more, and test it until I get the best output. And to measure the output, because I cannot go alone by the size of the breakout, I got this handy dandy little device that I made. It's an RF detector. It's really simple. This thing is dead simple. Just got a simple swing needle meter, and on the back, yeah, there's nothing to it. I mean, here's our antenna, which is this piece of wire here. Then there's a coil out of a switch mode power supply, and diode and a capacitor, and well, you know, that's it. That's the whole thing right there. A nice thing about that is it's self-powered, so it will run off the RF energy from the coil. And another thing I've added over here is a staccato circuit, just to make things a little bit easier on the tube, which is, again, really simple. All MOSFET based circuits. There's the MOSFET right there, and that's connected between the cathode and the ground. So now I can have staccato. Certainly can, yes, and it sounds a lot more like a Tesla coil now. And although you cannot really see it, it's even registering on the meter. Well, okay, I think we're just about ready to ramp this thing up now, because the red dot is where the coil was originally, and this dotted line is how much I've raised the coil by, because I just decided to mark each position of the coil, and I'd mark it with a green dot if the output was improved. So raise it up a little bit, test it, mark whether it got better or worse, and right about here we seem to get the best output. Now still nothing spectacular, but it is better. And hopefully this is not corrupting the data on my camera. And just out of curiosity, let's see this on constant wave again. So I've connected the cathode back up directly to the ground. I know it's all a bit how you're doing, but let's just have a look. There we are on constant wave. It looks a lot more impressive in real life than it does on camera. So we know that works. So now it's time to ramp it up with one of these. And instead of 500 volts, we're going to use 5,000 volts. Okay, well here we are in the shed, ready to go. Now I did try powering this off the 600 volt supply and that didn't do hardly anything. So I think it's going to fare a little better on the 5,000 volt supply. And I'll be honest with you, I haven't powered one of these on a microwave oven transformer without a ballast before, so that's what we're going to do right now. And we're armed and ready to go. I've got a remote switch, which I'm standing by. So let's turn it on and see if it works. Oh, that's not good. That's not good at all. Well, after that little bit of a scare, we're ready to try again. I've just noticed, I don't know if you can see it, but if I can just get the camera's light on there, you might be able to notice that the original paint that this had was a kind of a silvery paint. And I just thought this was white paint on wood. And it wasn't. So it was just arcing to the silver paint, and I cannot get my camera's light to come off. But hopefully we won't have any more short circuits. So let's try again. So like I fixed all the problems and I'm getting like huge arcs off this thing now. Right, so if I could just find some way to obscure this bulb so when that comes on, because when this is on there's enough current to make that bulb light up. So I've got to find a way to make that so it doesn't glare into the camera. And also, I think I need to improve the insulation here. Wood does not seem to be good enough. Okay, ready to try again. I've replaced all the insulation, so hopefully we shouldn't have any arcs where we don't want any. So, on with the show. Oh, if only it would show up on the camera. It's working wonderfully, but you just cannot. Oh, this camera sucks. Okay, so this is the last run for the day. Now, hopefully you'll be able to see it a lot better. So, let's see it in action one last time. Isn't it wonderful? Camera still sucks and can barely see it. It was just getting bigger and bigger and bigger. It was like this long. It was like that long, actually. It was huge. I had to turn it off there and then because I just noticed that my secondary was starting to break down and I noticed a little wisp of smoke coming off it, so yeah. Well, it would be rude to not try and get a proper shot of this, even though I don't know how much longer this is going to last. So, Here it is, one final time. I think that's all we're gonna get. Okay, I better shut it off now, because I think that's the end of my secondary. I popped it! Just a quick look at the aftermath there. You can see a little burn right there. And another burn around here. Smells nice. Anyway, there we go. That's building a vacuum tube tester coil the CoolDudeClem way. And until next time, goodbye.
I think that's all we're gonna get. Okay, better shut it off now, because I think